when you boil liquids, I don't care if it's water or I don't care what it is, the boiling point's always higher than the melting point. Always, no matter what the substance is. The amount of energy, this is 334 joules per gram. It takes 334 joules to melt 1 gram. But if you have 1 gram of water, it takes 2,260 joules. Again, joules is a unit of energy. I know I talk about bananas a lot, but it just helps. A banana has like 400 joules. So you could burn a banana and melt ice with it. There you go. Because you only need 334. You can't boil water with a banana. Not one banana. Maybe a bunch of bananas. Because as long as you get up to 2260, you can boil only 1 gram of water. It's a little tiny bit of water. Okay? So again, this takes way more energy to boil because when you boil, you are breaking forces apart. Here, melting, you're just weakening them. Okay? Solid particles are really close together. Look up here. Solid particles are really close, basically touching. Liquid particles are just a little bit further apart. It's not the distance that changes it from solid to liquid. What's the big change there? What can liquids do? Flow, move. Solids can't. That's the huge difference. So you're weakening the force here. Weakening versus breaking forces. Huge difference in energy. Okay? Again, the analogy we've used in here in the other class. Hugging is like a solid. Shaking hands is like a liquid. A gas is if you have no contact at all. So you're like breaking your handshake. That's what it takes, a lot of energy to do that. All right? You're still really close together as a liquid. You're just able to move around more. Okay? So I know I feel like I'm repeating a lot today, over and over different things, but it's important to understand the concepts and not just memorize. All right? So that's why boiling takes more energy, because you're breaking forces. All right. So what we're going to do the rest of the period is I'm going to give you sample problems to use these Q equations, and that's what the lab's going to do. So in the lab, you're going to get this on your iPad, and then you're going to look at the graph and look at the temperatures and get the mass of the ice, and you're going to use these 3 equations. All right? So I'm going to erase this, and we're going to, first we'll practice Q equals mc delta T, and then we'll do one of these melting and one of the boiling. So we're going to practice using that equation, all 3 equations that we've talked about. All right, so you do need your calculator for this. I don't want you using a phone, so you can use one of these cheesy ones. All right, and before we actually get into a calculation, though, I need to explain this number here. 4.18 joules per gram Celsius, that's C, the specific heat of water. Specific heat, write this down, please, capacity. Capacity of H2O, that's 4.18. There's a worksheet you're going to be doing. Let me tell you what the specific heat capacity of iron is. So iron is 0.45. So the C for iron is 0.450 joules per gram degrees Celsius. Okay. All right. A couple analogies here. I want you to understand what this unit, like what does this mean before we get into calculations. Anybody have a pool? You have a pool? You have a pool? In ground? Above ground? All right. Well, you got anything around it, or is it just like in the middle of the lawn? No, like a deck around there or something like that? Yeah. All right. Well, have we all been to a pool in our life? Okay. I don't have a pool. My in-laws do. Okay. Let's imagine, I guess we could all be at Sean's pool. Yeah, we're all at Sean's pool. All right. You got, I don't know.
He was showing.
You got a big enough deck for everybody?
I have a 38 by 20.
I guess. All right. Okay. So let's say it's middle of summer. Let's say it's 105 degrees out. Okay? We're all standing on the deck, bare feet. What's the problem?
Hot.
Yeah, you're probably going to burn your feet. Would you agree the deck gets pretty hot? You ever been on a hot deck? Okay. So what are we going to do?
Jump in the pool.
Jump in the pool. Okay. Jump in the pool. The pool is hot as the deck.
No.
that would defeat the point of having a pool, right? Defeat the purpose. Okay. Good. Let's say you're at an in-ground pool. We're all standing on the sidewalk around the pool. It's 105 degrees out. No clouds in the sky. Think it's a little bit hot on the concrete? Yeah. I mean, that'll literally burn your feet very quickly. So you jump in the pool. Is the pool as hot as the concrete? Okay. You ever stand on pavement with bare feet in the middle of summer, 105? Okay. Wicked hot. Okay. Let's say you're on the road. It's really, really hot. You want to get off the pavement. Where would you go? The grass! Is the grass as hot as the pavement? No.
The pool.
The pool on the side of the road, right? What am I trying to explain? You ever heat something up in the microwave and it just seems to stay hot forever? Like you're hungry or you want to drink it or whatever and it just won't cool down, but then some things cool down very quickly. I don't know if you've ever just noticed in life in general. Yeah? Okay. It's the same. All of that is related. Okay. Look at the numbers. Water, 4.18. Iron, 0.45. I just had a thought.
That was funny.
I had a good thought. I'm going to give you a specific heat of concrete.
Of what?
Concrete. Here we go. 1 point. That's not right. I thought it was going to be quicker. Here we go. 0.92. So concrete is 0.92 joules per gram degree Celsius. That's the specific heat of concrete. All right. It's worth spending a little time because this is like practical knowledge, actually. It's not, forget the regents and all that jazz. It's important to know, why the heck is the concrete or the deck so hot and the water way cold?
Is it because it has to do with like the solid and like liquid thing?
Sort of.
Takes more energy to heat water.
Yes, it takes a lot more energy. That's what these numbers tell us. That's exactly what these numbers tell us. If you have a gram of concrete and a gram of water and a gram of iron, the iron will heat up faster than the other three, very quickly. What this number tells us is you only need 0.45 joules to heat up 1 gram of iron, 1 degree Celsius. That's what this tells us. But you need 4.18 joules. So you need way more energy to heat up water than you do iron or concrete. So iron, metals, heat up fast. I think you probably know that. You can put a pan on top of a burner and turn the burner on low. I mean, it heats up almost instantly to the point where you can't touch it. All right, so we make pots and pans out of metal because they heat up very well. They conduct heat very well. That number is really small because of that. Concrete also heats up very fast, but things like dirt, grass, water, they don't heat up very fast. So you need way more energy. So besides the fact the pool is water, there's also a huge amount of it compared to a little bit of iron or concrete or wood or whatever your deck is made of. But that's what this tells us. So this number is unique to water, and water has an extremely high specific heat. So anything that takes a long time to heat up and a long time to cool down, this is why. There's an actual number assigned to it. Think of a food. It takes a long time to heat up and a long time to cool down. I had some this morning. It stays hot forever. Okay, coffee. Oatmeal, yeah, oatmeal seems to stay hot for a long time. Do you agree? Yeah, you don't pay attention. But yeah, so certain foods will have higher specific heats than others. Think of it that way. So so I had quinoa for dinner last night. Shocker. It cools off so fast. It's annoying. Sometimes I think to myself, man, wish specific heat was a little bit higher. Anyways.
You're sitting there at the dinner
That's
table
what
and
you
you're
think
like, oh, I
about
wish
me,
it
and
was
I
So
wish
in
it
my
was
head,
specific
I don't
heat.
say these things out loud like a weirdo. But I use the analogy, and it's funny, and I tell stories. And kids remember that stuff, though. I talk about food, and hopefully you remember that. So specific heat capacity, again, it takes 4 joules to heat up water, and it has to lose it. So if water wants to cool down, it needs to lose that. So let's use the analogy again. We're all at Sean's. This time it's midnight. Same day. Okay? Same day. It was 105 during the day. We're on the deck. Can't even stand out. It's so hot. Going to pool. Now, it's midnight. That same day. What's going on with the deck and the water?
The deck is cooler than the water.
Deck's probably going to be cold, actually. And the water's going to be
Warm.
warm. Because of what you said. Water takes a long time to heat up. But guess what? It takes a long time to cool off. If you've ever gone swimming at night, isn't the water always warm? Warmer than the air temperature? Almost always. That's why. Water retains its heat very well. If you boil water, coffee, tea, you made it really hot, it takes a long time for it to cool down. This is why. It's not just like magic or because of the way it is. It's because the particles in water, the way they're packed together, and the chemical properties, it loses energy very slow. So it has to lose 4 joules. These only lose 0.45 and 0.92 when they're cold. So, in the city, manhole covers, crazy hot during the day, but at night they're really cold. And that's because they lose all their energy very quick, made of metal. You may not know that, but whatever. Now you do. So, that's an important concept. What does that number mean? That's what it means. I have one more question for you. If you live in the middle of the country versus the coast, now let's assume same latitude. So, I don't know, say Boston and whatever the heck the middle would be, maybe, I don't know, Boston's a little too far north. Let's go New York City and then somewhere in the middle of the country. I don't know, pick something in the middle of the country. Kansas is probably too low. I don't know. So anyways, the difference between the middle of the country and the coast is the middle of the country doesn't have any water. There's no ocean. You guys know that. How does that affect the weather?
Because there's like wind on the coast. Like,
There's a lot more wind and breeze on the coast.
is that because like the, forget it.
Okay.
Doesn't that have to do with like the tides?
More dry without the ocean. Very good. That's not where I'm going, but yep. Why is there more wind? What creates wind?
The God, I don't
Pressure
know.
changes, but
I don't know what creates wind.
more importantly, it's temperature changes. So if you're at the ocean in the summer, usually you feel a cooler breeze coming from the ocean. I don't know if anyone's paid attention. Yeah. So the air, the breeze coming from the ocean is cooler than the air on land. And that's fact. Whether you believe me or not, or you pay attention, that's just the way it is. This is why. Above the ocean is cooler than above the land. Because here's the land, heats up super fast, cools off super fast. Water heats up slow, cools off slow. So where am I going with this? I want you to try and connect the dots. Think of the weather difference in the middle of the country versus the coast. Think of summer, think of winter. What's the advantages of living on the coast in the summer and the winter? Just living on the coast, period, with your weather versus the landlocked. Where is it colder
On
in
coast.
the winter?
By the ocean.
The center of the country.
Is it really? That doesn't make sense.
Okay, I'm gonna put water on the stove. I'm gonna boil that water. Okay, that's the summer. I'm gonna take that off, put it on the desk. That's the winter as it cools down. The pot is the ocean. I'm trying to be vague. I want you to connect the dots on your own. What does the ocean spend all summer doing?
Heating up.
Heating up.
So it's gonna take a long time.
Then in this winter time, it's releasing all of its heat. It's like this the pool during the day. So we're standing on his deck in the middle of the day. That's summertime. The ocean is nice and cool. So we get cool breezes from the ocean. In the winter time, that's like at nighttime on the deck. The land is cold, but the water is warm. So how are the temperatures different? If you're landlocked, your winters are really, really cold. Your summers, really, really hot. There's no water. There's no water to absorb or release the heat. In the summer, the ocean takes a lot of heat. So the coast is much cooler. And in the winter, it releases that. So the winters are definitely warmer on the coast. and this isn't like crazy, like me making this up. If you were to look at, years and years averages of temperatures, coastal cities have cooler summers and warmer winters than landlocked, the central part of the United States. And it's all because of this number. That's the whole point of this conversation. Because water's specific heat is pretty high, really high compared to most common materials, that's why. Okay? So it's important that I talk about it because I think it's relevant information. That's why coffee stays hot so long. That's why the pool feels warm at night. Okay? I think it's cool to know these things, not just be like, oh, water's warm, whatever. Now you know why. It's because it's retaining all that heat. And a lot of people may know it, but now you know the actual reasons because of that number. All right? So hopefully some of that was fairly interesting. Thanks, Sean, for letting us come over. Sorry, Karen. All right. Basically out of time. Huh? All right, we'll stop there, but don't fear. You have homework. So tomorrow we will do calculations. I promise. All right. Front and back. You're basically just labeling this thing.